Our Milky Way galaxy, along with countless others, is not just idly floating through space. Instead, it is moving, pulled by forces that extend far beyond our immediate cosmic neighborhood. One particularly intriguing destination, or rather source of attraction, is what astronomers have named the Great Attractor, a mysterious gravitational anomaly affecting the motion of galaxies across a vast region of space. To understand the significance of this discovery, we need to explore how galaxies move and what causes them to gravitate toward certain areas. Galaxies are rarely found in complete isolation. They tend to group together in clusters and superclusters, with gravitational forces binding them over millions of light years. Gravity is the fundamental reason why galaxies cluster. Massive collections of stars, gas, dust, and dark matter exert a pull that influences neighboring galaxies' trajectories. However, some movements defy explanations based solely on observable mass within known clusters. The Great Attractor represents such a puzzle. It appears as a colossal gravitational focal point to which hundreds of thousands of galaxies seem to be moving, yet much about it remains hidden. To grasp this concept more vividly, picture the cosmic web, an arrangement of filaments composed of dark matter and galaxies threading through the universe, with vast voids between them. Within this network, gravitational interactions guide the flows of galaxies like rivers toward basins. The Great Attractor lies within or near the center of such a basin, exerting a pull felt across hundreds of millions of light years. Early observations in the late 20th century uncovered that our galaxy and its neighbors do not merely drift with the overall expansion of the universe, but have a significant motion relative to this expansion. This difference is called a peculiar velocity, indicating movement aside from the universal push caused by cosmic expansion. When astronomers measured how fast galaxies moved, they noticed a consistent pattern. Galaxies, including the Milky Way, seem to head toward a specific patch in space centered around the constellation Centaurus and Norma. This motion toward the Great Attractor is surprisingly swift. Our galaxy is moving toward this region at approximately 600 kilometers per second, about 1.3 million miles per hour. Such speed, in cosmic terms, is quite notable and cannot be explained by the gravitational influence of nearby objects alone, like the Local Group or the Virgo cluster, which includes the famous Andromeda galaxy. Instead, there's something far more massive pulling galaxies collectively over immense distances. But despite this compelling evidence for a massive gravitational source, the Great Attractor itself proves stubbornly elusive. This difficulty is primarily due to the plane of our own Milky Way, filled with stars, interstellar dust, and gas clouds that obscure our view of the region behind it. Astronomers call this obstructed area the zone of avoidance. Penetrating this veil requires sophisticated observations at wavelengths that can pass through dust, such as X-rays and radio waves, rather than traditional visible light. Using such methods, astronomers have mapped part of the region around the Great Attractor, discovering enormous structures dense with galaxies. The Norma cluster, for instance, is a sizable galaxy cluster near the heart of this area, contributing significantly to the gravitational pull. Still, even when accounting for all known masses in this region, the amount of visible matter doesn't seem to explain the total force exerted on the Milky Way and other galaxies. This discrepancy suggests there might be additional unseen mass, possibly vast clouds of dark matter or other large-scale structures, hidden within the zone of avoidance. Dark matter, an invisible and mysterious form of matter that neither emits nor absorbs light, makes up the majority of matter in the universe and plays a crucial role in shaping the cosmic web and the formation of galaxies. Its presence is indirectly inferred by its gravitational effects, including the anomalous motions toward the Great Attractor. To better understand the Great Attractor, scientists have engaged in several extensive surveys using different telescopes and instruments. The ROSAT satellite, for example, observed X-ray emissions from galaxy clusters behind the Milky Way's obscuring dust, revealing many hot gas clouds that indicate dense collections of matter. Surveys like 2MASS, which maps the sky in infrared, help detect thousands of galaxies otherwise hidden in visible light. Yet the story grows even more fascinating when we consider that the Great Attractor itself might not be the ultimate source of this cosmic tug. Later studies propose the existence of even larger structures beyond it, superclusters and cosmic superstructures with a titanic grasp. One prominent example is the Shapley supercluster, a gigantic concentration of galaxy clusters located beyond the Great Attractor. Some research suggests that the Shapley supercluster exerts a significant gravitational pull, possibly even stronger than that of the Great Attractor, influencing the flow of galaxies in our region of space. This layered structure of gravitational influences highlights the complexity of cosmic motions and challenges straightforward identification of the primary sources exerting these forces. In other words, the Great Attractor is part of a hierarchy of structures along the cosmic web, and the Milky Way's motion probably results from the combined pulls of superclusters and clusters spread across hundreds of millions of light years. Understanding these motions matters beyond mere curiosity about our cosmic address. The way galaxies move and cluster holds vital information about the fundamental properties of the universe, its composition, structure, and history. For example, measuring the peculiar velocities of galaxies can help scientists estimate the amount and distribution of dark matter, test theories about cosmic expansion, and refine the famous Hubble constant, which dictates how fast the universe is growing. Moreover, the Great Attractor challenges astronomers to develop better tools and methodologies to peer into obscured regions, pushing technological advances. Radio telescopes, infrared detectors, and X-ray observatories all contribute to peeling back the curtain on these hidden structures. Future missions, such as more sensitive space telescopes and extensive galaxy surveys, promise to enhance our understanding further. In the meantime, the Great Attractor remains a striking example of how much about the universe is still unknown, even in regions relatively close to us on the cosmological scale. It is a reminder that the cosmos is a dynamic and interconnected system, where gravity molds the architecture of clusters, superclusters, and supervoids. As our techniques advance and our observations become more precise, scientists continue to uncover the complex gravitational landscape shaping the universe's large-scale motion. Each discovery about anomalies like the Great Attractor brings us one step closer to a more complete picture of the cosmic web and our place within it. Continuing the exploration into cosmic flows, the study of our galaxy's motion inevitably ties into the vast bulk flows of galaxy clusters, phenomena where groups of galaxies move coherently in the same direction at substantial velocities. These bulk flows can extend across vast volumes of space, tracing the underlying mass distribution of the universe. The Great Attractor represents a crucial piece of the puzzle, helping decode the origin and nature of these large-scale motions. Understanding these motions requires developing sophisticated computational models and comparing simulations rooted in our current cosmological frameworks, such as the lambdictum model, lambda cold dark matter, which incorporates dark energy, lambda, and cold dark matter as the dominant components of the universe. Simulating galaxy evolution, along with the cosmic web formation, helps to interpret observational data and pinpoint how features like the Great Attractor form and affect their surroundings. The interactions and mergers within superclusters, along with the role of dark matter halos, highlight the intricate dance underlying galaxy motions and the fabric of spacetime itself. Each new observation sheds light on these mysterious forces that silently steer galaxies on their paths. In scientific terms, our quest to understand the Great Attractor exemplifies the interplay between observation and theory, inviting us to explore beyond the visible and embrace the unseen forces that shape our universe. The gravitational pull we experience is a tangible connection to these invisible giants, and this pursuit continues to refine our cosmic map, making the universe a little less mysterious and a lot more fascinating. An important aspect of the story surrounding the Great Attractor revolves around the role of dark matter, an unseen substance that permeates the cosmos and exerts gravitational influence without emitting light or any form of electromagnetic radiation. While ordinary matter, the stars, gas, dust, and planets we can observe, accounts for only a small fraction of the universe's total mass, dark matter forms the backbone of large-scale structures like galaxy clusters and superclusters. It is the invisible scaffolding on which galaxies assemble and cosmic patterns emerge. The significance of dark matter when investigating phenomena like the Great Attractor cannot be overstated, since the gravitational pull driving the motion of galaxies toward this massive region appears far stronger than what can be explained by visible matter alone. Astronomers infer that a substantial amount of mass must be dark, hidden from direct view, but detectable through its gravitational effects. This line of reasoning aligns with a growing body of evidence supporting dark matter as a dominant component shaping the universe's architecture. To better grasp this concept, imagine the cosmic web as a vast, three-dimensional network of filaments composed primarily of dark matter, with galaxies and gas clouds tangled along these threads. Massive concentrations of dark matter within this web generate strong gravitational wells, acting like gravitational attractors that draw nearby galaxies toward them. The Great Attractor resides in one such well, embedded deep within this complex network. Its influence stretches over hundreds of millions of light years, reshaping the motion of galaxies, including our own Milky Way. In fact, the motions we observe are not random drifts, but are guided by gravity's pull along these filaments and nodes. Peculiar velocities, the deviations of galaxies' motions from the general expansion of space, result from such tugs, while the universe itself is expanding, causing galaxies to move apart on average. Gravitational attractions induce local accelerations, pulling galaxies together in clumps and clusters, momentarily overcoming cosmic expansion at these scales. This interplay explains why the Milky Way and its surrounding galaxies fall toward the Great Attractor. Pinpointing the exact nature and composition of the Great Attractor region, however, has proven challenging due to its location behind what astronomers call the zone of avoidance. This is an area of the sky obscured by the dense plane of our own Milky Way, where clouds of dust and gas block optical light and complicate direct observation. To overcome this hurdle, researchers rely on alternative wavelengths beyond visible light, especially infrared, radio, and X-ray observations, which can penetrate the obscuring material and reveal the hidden structures lurking behind. Surveys like the 2-micron all-sky survey, 2MASS, have been invaluable in mapping galaxies in this zone of avoidance, laying bare thousands of objects that were previously invisible due to dust interference. Infrared light, which has longer wavelengths than visible light, manages to slip through the dust more effectively, enabling astronomers to identify galaxies forming part of the Great Attractor's domain. Similarly, radio wave observations, particularly using the 21-centimeter hydrogen line, a spectral signature of neutral hydrogen gas, can detect galaxies beyond the Milky Way's dense clouds. Another critical window into this region is provided by X-ray astronomy. Many of the clusters within and around the Great Attractor emit X-rays due to the extremely hot gas trapped within their gravitational fields. This hot gas is heated to millions of degrees Kelvin, and its X-ray emission shines through galactic dust almost unimpeded. Instruments like the ROSAT and the Chandra X-ray Observatory have revealed numerous galaxy clusters in the zone, helping build a clearer picture of the mass and structure involved. Among the key structures identified in this region is the Norma cluster, Abell 3627, a colossal cluster of galaxies situated near the heart of the Great Attractor. It is one of the most massive galaxy clusters in the nearby universe and a prime candidate for the core of the Great Attractor's gravitational well. The Norma cluster hosts thousands of galaxies bound together by gravity and contains enormous amounts of hot, X-ray-emitting gas. Its mass alone could account for much of the gravitational pull observed. Yet, even with Norma's weight, studies indicate additional contributions must come from other, more distant mass concentrations. This insight leads us to consider the scale and interconnectedness of cosmic structures as a key to understanding the Great Attractor's influence. Rather than a single point source, the Great Attractor is better thought of as a region or concentration of mass spread across a range of space within a supercluster environment. Our galaxy's motion is pulled by the combined gravitational attraction of many massive galaxies, clusters, and superclusters aligned along our direction of motion. Advancing farther into these depths, astronomers have recognized that beyond the Great Attractor lie even more massive assemblies, most notably the Shapley supercluster. Located about 650 million light-years away from Earth, the Shapley supercluster is one of the most massive structures in the nearby universe, containing dozens of galaxy clusters packed into a dense region. Its gravitational influence likely plays a major role in the overall flow patterns of galaxies, including the Milky Way's movement. The presence of the Shapley supercluster complicates the picture by suggesting that the Great Attractor, while significant, is not the final destination or the ultimate puller of galaxies. Instead, it might be an intermediate waypoint in the broader cosmic current pulling objects toward the densest matter concentrations in the universe. This hierarchical structure mirrors our understanding of the universe as a giant web, where clusters coalesce into superclusters, which in turn connect into even larger conglomerations. Astrophysicists simulate this behavior using computer models that start from the early conditions of the universe, approximately 13.8 billion years ago, and evolve millions of particles representing dark matter and gas over cosmic time. These simulations recreate the formation of the cosmic web and show how mass aggregates along filaments into the structures we observe today. By adjusting parameters to match observed galaxy distributions and motions, researchers can test hypotheses about how features like the Great Attractor form and influence their surroundings. One aspect frequently emphasized in these studies is the role of dark energy, a mysterious force causing the universe's accelerated expansion. While dark energy pushes galaxies apart on the largest scales, the gravity of massive structures like superclusters counteracts this to varying degrees locally. Understanding the balance between these forces aids scientists in building a coherent picture of cosmic evolution, from the Big Bang to the current epoch. Delving into galaxy dynamics reveals additional complexity, as individual galaxies are not simply test points moving under gravity, but rather active systems capable of interaction, merger, and star formation. Within superclusters and clusters, galaxies can collide and merge, altering their shapes and triggering bursts of star creation or the formation of supermassive black holes at their centers. These processes impact the distribution of visible matter, gas, and energetic radiation, further informing observations. Returning to the Milky Way's story, the Great Attractor is a reminder that our galaxy is not isolated, but part of a vast, interlinked system shaped by these enormous gravitational forces. While we orbit the center of the Milky Way, we and our neighboring galaxies collectively fall toward the Great Attractor at speeds of several hundred kilometers per second relative to the cosmic microwave background, the faint glow left over from the Big Bang. This motion is detectable as a dipole pattern in the cosmic microwave background radiation's temperature, a subtle but measurable shift signaling our movement through space. The ability to measure this motion with such precision stems from remarkable advances in observation technology and data analysis. The cosmic microwave background, first discovered in 1965, has since been mapped in exquisite detail by missions like COBE, WMAP, and Planck, enabling astronomers to interpret these dipole wiggles as indicators of our galaxy's velocity. Combining these measurements with galaxy surveys creates a comprehensive picture of large-scale motions within our cosmic neighborhood. Understanding the Great Attractor also holds practical implications for the field of cosmology. Since gravity is the only force shaping structures on the largest scales, mapping peculiar velocities and the underlying matter distribution helps refine the values of critical cosmological parameters, including the total matter density of the universe and the nature of dark energy. Such insights feed into models predicting the fate of the cosmos, whether it will continue expanding forever, slow down, or eventually contract. Moreover, investigating the Great Attractor pushes the boundaries of astrophysical techniques, inspiring new instruments capable of penetrating obscured regions and detecting fainter, more distant objects. Collaborations between ground-based observatories and space telescopes broaden the wavelength coverage, while improvements in computational power allow simulations to reach unparalleled resolution and realism. Even today, future projects promise to deepen our understanding. The upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSSD, will provide an unprecedented wide and deep mapping of galaxies across the sky, including those in and beyond the zone of avoidance. At the same time, proposals for infrared and radio observatories positioned beyond Earth's atmosphere aim to reduce interference and achieve greater sensitivity, potentially revealing finer details of the structures involved. In summary, the Great Attractor exemplifies the complexity inherent in our cosmic surroundings. It is not a single object, but a vast gravitational nexus embedded within a larger hierarchy of matter concentrations woven into the cosmic web. Dark matter's unseen hand, obscuring foregrounds, and the interplay of local gravity with cosmic expansion all converge to define our galaxy's motion and place within the universe. This intricate dance challenges astronomers to continually refine their instruments and theories, turning the mysterious and inaccessible into domains of active research and discovery. While much remains to be learned, each new piece of evidence brings us closer to understanding the forces shaping the galaxies, including our own and their journeys through the universe. Despite the progress made in exploring the Great Attractor and its role in the movement of our galaxy, there remains a significant observational challenge. Much of the region containing the Great Attractor is concealed behind what astronomers call the zone of avoidance. This area of the sky is heavily obscured by the dense plane of the Milky Way, which is filled with gas, dust, and countless stars. This veil blocks visible light from reaching us, making it difficult to see the structures lying beyond. As a result, traditional optical telescopes provide an incomplete and patchy picture of the mass lurking behind our own galaxy's disk. To work around this limitation, astronomers turn to other parts of the electromagnetic spectrum, particularly X-rays, infrared, and radio waves, that can penetrate the dense gas and dust clouds. Observations in these wavelengths have revealed important details about the clusters of galaxies and the large-scale structures hidden in the zone of avoidance. For example, X-ray emissions, which often originate from hot gas trapped in the gravitational wells of galaxy clusters, provide vital clues about the distribution of matter where visible light cannot reach. One of the most prominent discoveries in this effort is the Norma cluster, also known as Able 3627. Residing deep inside the zone of avoidance, the Norma cluster is one of the largest and most massive galaxy clusters in the nearby universe. Studies show it contains thousands of galaxies, some of which display signs of ongoing interactions and mergers, illuminating the dynamic processes at work within these bound systems. The cluster's gravitational pull is thought to contribute substantially to the Great Attractor's overall mass, making it an essential piece of the puzzle. Yet, even the apparent richness of Norma alone doesn't fully explain the Great Attractor's pull. Instead, it appears that the Great Attractor encompasses a complex web of galaxy clusters, groups, and superclusters, wispy filaments weaving through space that collectively create a gravitational attraction powerful enough to influence motions across hundreds of millions of light years. This interconnected system highlights the hierarchical nature of cosmic structures, where smaller components build into larger complexes. In parallel with direct observations, redshift surveys have become powerful tools for mapping these structures. Redshift occurs when light from distant galaxies shifts toward longer wavelengths due to the expansion of the universe, allowing astronomers to estimate their distances and spatial distribution. Modern surveys, such as the 2-mass redshift survey and the 6DF galaxy survey, have effectively cataloged hundreds of thousands of galaxies, including those approaching or receding due to local gravitational effects rather than just cosmic expansion. Interestingly, these redshift surveys give rise to what's known as peculiar velocities, deviations from the expected motion driven solely by the Hubble expansion, the stretching of space that pulls galaxies apart. Peculiar velocities indicate local gravitational forces at work, often pointing toward attractors like the Great Attractor or even more distant structures. By analyzing these velocity fields, scientists use the galaxies themselves as tracers to map the underlying distribution of both visible and invisible matter. A key development in this area involves reconstructions of the density and velocity fields of the local universe, which require sophisticated mathematical techniques and computer modeling. Through these reconstructions, researchers have identified a larger superstructure called Laniakea, our home supercluster of galaxies, which spans over 500 million light-years and encompasses the Great Attractor as one of its massive gravitational nodes. Laniakea represents a significant advancement in understanding the gravitational landscape surrounding the Milky Way, revealing that rather than moving randomly, our galaxy is part of a coherent flow toward a larger cosmic basin. Dark matter, an invisible and mysterious form of matter, is the silent but dominant actor in this story. It does not emit, absorb, or reflect light, yet its gravity shapes the formation and behavior of galaxies and clusters. Studies indicate that dark matter must exist in substantial quantities within and around the Great Attractor, anchoring the galaxies and pulling them inward. This notion stems from measurements of galaxy motions and cluster dynamics, which cannot be explained by the mass of visible matter alone. The nature of dark matter remains one of the biggest open questions in physics and cosmology. Leading candidates include weakly interacting massive particles, WIMPs, and axions, but definitive detection has so far eluded scientists. Regardless of its exact identity, dark matter's gravitational influence is clear. It is responsible for the observed clustering of galaxies and the overall shape of the cosmic web, including the massive, hidden concentrations of matter like that comprising the Great Attractor. In addition to dark matter, hot gas trapped between galaxies and clusters contributes to the total mass exerting gravitational influence. This intracluster medium reaches temperatures of tens of millions of degrees and emits strongly in X-rays. Observations by X-ray telescopes, such as NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton, have mapped this hot plasma within clusters related to the Great Attractor region, refining mass estimates and revealing the energetic environment of these massive structures. It is the combined gravity of all these components, dark matter, galaxies, galaxy clusters, and hot gas, that generates the gravitational well we call the Great Attractor. While it remains challenging to pinpoint all its details due to observational limits, advances in multiple wavelengths, stellar surveys, and computer simulations continue to improve our understanding. Beyond the Great Attractor, even larger structures exert influence on galaxy motions, highlighting the vast potential scales involved in cosmic flows. The aforementioned Shapley supercluster, positioned tens of millions of light-years beyond the Great Attractor, is one such massive complex playing a key role in the motion of galaxies, including our Milky Way. The recognition of multiple attractors and the notion of hierarchical flows reshape our perspective on cosmic dynamics. Galaxies do not simply orbit isolated clusters, but participate in layered motions influenced by vast networks of matter interconnected across space. Moreover, these flows inform cosmologists about the fundamental composition of the universe. By comparing observed peculiar velocities to predictions based on different cosmological models, they constrain the amount and distribution of dark matter and dark energy. This approach complements studies of supernovae, the cosmic microwave background, and gravitational lensing, progressively tightening our understanding of the cosmos. Another intriguing aspect is the relationship between the Great Attractor and supermassive black holes. While the central gravity of the Great Attractor is not due to a single black hole, as is the case in galaxies, it resides in a region of clustered galaxies, many of which harbor black holes millions or billions of times more massive than the Sun. These black holes can impact their immediate surroundings, influencing star formation and gas dynamics within their host galaxies. Though their spheres of influence are comparatively small relative to the scale of galaxy clusters, understanding these dynamics is part of the broader effort to comprehend how matter behaves on multiple cosmic scales. The entangled interactions within and around clusters associated with the Great Attractor also provide laboratories for testing theories of galaxy formation and evolution. Galaxy collisions, mergers, and the stripping of gas during cluster infall change the shapes and star formation rates of galaxies. These processes are recorded in galaxy properties observed across electromagnetic wavelengths, linking the local dynamics to the large-scale gravitational framework. In essence, the Great Attractor is a focal point where our understanding of galaxy dynamics, dark matter, cosmic structure, and cosmology converge. It exemplifies how much remains to be uncovered, even within the relatively nearby universe. The coordinated efforts of astronomers, using a range of observational techniques and theoretical tools, continue to peel back layers of mystery. The coming years hold promise for refining this picture. Projects like the Vera C, Rubin Observatory's Legacy Survey of Space and Time, LSSD, will map billions of galaxies over a decade, improving distance estimates and uncovering faint galaxies within obscured regions. Meanwhile, future space telescopes, equipped for infrared and radio observation, aim to penetrate even deeper into dust-shrouded zones. On the computational side, exascale computing will enable simulations with higher resolution and physical sophistication, integrating baryonic physics, the behavior of normal matter, dark matter, and cosmic expansion to predict observable properties and test ideas against rich datasets. Understanding what propels the Milky Way and its neighboring galaxies toward the Great Attractor provides a window into the forces that shape our universe. Far from being stationary or isolated, our galaxy participates in a complex dance along invisible currents traced by gravity. The Great Attractor serves as a reminder of the unseen wealth of structures and matter influencing this motion, challenging us to expand our vision and techniques as we explore the cosmic landscape. To grasp the significance of the Great Attractor, it's important to consider the broader context of how galaxies move through space. Our Milky Way doesn't just orbit its center or slowly float through an empty void. It's part of a vast cosmic web of matter, shaped by gravity, where groups of galaxies influence each other's movements. The peculiar velocity of the Milky Way, how fast and in which direction it moves relative to the cosmic microwave background radiation, is a direct clue that something massive lies ahead, pulling on us and neighboring galaxies with gravitational force. This motion toward the Great Attractor is measured relative to the background expansion of the universe, which itself is governed by the Big Bang and the ongoing accelerated stretching driven by dark energy. Galaxies are receding from each other due to this expansion, but the peculiar velocity adds an extra component, an additional speed and direction caused by local gravitational influences. For the Milky Way, this peculiar velocity is about 600 kilometers per second toward the general region of the Great Attractor. What's fascinating is that this flow of galaxies is not random. Instead, it reflects the uneven distribution of matter, with dense regions exerting stronger gravitational pulls. Mapping these flows involves studying redshifts and distances of galaxies to identify deviations from uniform expansion. These deviations are crucial. They let astronomers reconstruct the matter distribution in the universe, even in regions where direct observations are challenging. It's a bit like feeling the pull of an invisible anchor in the ocean, even if you can't see it yourself. But the Great Attractor itself, while dense and massive, isn't the deepest gravitational well in our cosmic neighborhood. Beyond it lies the Shapley supercluster, an even more massive assembly of galaxy clusters. The Shapley supercluster lies some 650 million light-years away, much further than the Great Attractor, yet it still exerts influence on galaxy motions within our local supercluster region. This hierarchy of structures, from individual galaxies to clusters to superclusters, creates a layered landscape of gravitational forces that shape large-scale motions in the universe. The complexity of these flows highlights an important fact. The cosmic map of matter density isn't uniform or simple. Instead, it's patchy and interconnected, with voids, large regions with fewer galaxies, interspersed among filaments and nodes where galaxies and clusters congregate. This structure is sometimes referred to as the cosmic web, shaped during billions of years of gravitational collapse and expansion. It is within this web that the Great Attractor resides as one of the prominent concentrations influencing local motion. Our ability to create three-dimensional maps of the nearby universe, including the region of the Great Attractor, has improved dramatically in recent decades. Galaxy surveys such as the 2-micron All-Sky Survey, 2MASS, and the Sloan Digital Sky Survey, SDSS, have mapped millions of galaxies, revealing intricate structures. Yet they face challenges because the Great Attractor lies in the direction of the zone of avoidance. This is a part of the sky where the dense plane of our own Milky Way obscures distant galaxies, blocking visible light and complicating observations. To overcome this, astronomers rely on observations at other wavelengths, especially infrared and radio. Infrared light can penetrate dust clouds that obscure visible observations, allowing hidden galaxies to be detected behind the Milky Way's disk. Similarly, radio wavelengths can reveal emission from neutral hydrogen gas, often present in galaxies, offering another pathway to map this elusive region. These multi-wavelength observations complement each other, gradually filling in the map where optical light falls short. One remarkable result from these studies is the confirmation that the Great Attractor region contains a massive concentration of galaxy clusters, collectively weighing hundreds of trillions of times the mass of our Sun. The Norma cluster, also known as Abell 3627, is among the most significant clusters in this region and is often regarded as the heart of the Great Attractor. This cluster alone contains thousands of galaxies bound together by gravity, and it sits near the center of that localized gravitational well. While individual galaxies within these clusters can be studied in detail, their motions are also influenced by the cluster's total mass, which includes stars, gas, and dark matter. The observed velocities of galaxies within clusters help astronomers infer how much unseen matter is present, complementing efforts to estimate the cluster's gravitational pull on the Milky Way and its neighbors. The Great Attractor is, therefore, not a single object or entity, but a vast concentration of matter made up of many components. It is a gravitational hub pulling galaxies toward it, but it is also connected to larger-scale structures encompassing even more matter. Understanding these relationships is essential because it places the Milky Way's movement within a broader cosmic journey. As we look ahead, upcoming missions and surveys promise to clarify the nature of the Great Attractor and its surroundings even further. For instance, the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, will detect gravitational waves from merging black holes, including those residing in clusters near the Great Attractor. These data could offer insights into the population and behavior of massive black holes in such dense environments. Similarly, continuing improvements in spectroscopy, that is, analyzing the light from galaxies to determine their distances and velocities, will sharpen maps of galaxy flows. Enhanced computational models integrating observational data allow theorists to simulate large volumes of the universe, reproducing galaxy motions that match those observed. These simulations offer a testbed for theories about how dark matter shapes structure and provide predictions that can be compared to real measurements. The Great Attractor also illustrates the way scientific understanding evolves. When it was first identified in the 1980s, the exact nature of this gravitational pull was a mystery cloaked behind dust and distance. Over time, successive waves of observation and theory have fleshed out a clearer picture. The Great Attractor is a complex node within the cosmic web, a vast congregation of clusters and material influencing galaxy motions on a scale that spans hundreds of millions of light years. More broadly, this story reveals how astrophysics highlights the interconnectedness of phenomena across scales. From the behavior of individual stars and black holes within galaxies to the way entire clusters and superclusters interact gravitationally. Our position in the universe is not isolated. Rather, it's woven into the dynamic structure of matter itself. Another important area where the Great Attractor has left its mark is in the study of cosmography, the mapping of the universe's structure. By charting out the directions and speeds of galaxies as they move toward these massive attractors, astronomers can construct flow maps that reveal the density and arrangement of matter. These flow fields are key to understanding the process of structure formation, telling us where matter has gathered and where it has been pulled away. Flow maps also reveal the presence of voids, enormous bubbles where few galaxies reside. These voids influence motions just as much as dense clusters, because galaxies at their edges tend to move away from them, drawn toward nearby concentrations of matter. The Great Attractor is one of several regions where competing gravitational effects direct galaxy motions, creating a complex pattern of cosmic currents throughout our local volume of space. Considering the scale of these structures and their influence, the Great Attractor is a testament to the power of gravity to shape the universe on the grandest scales. It affects not only our galaxy's trajectory, but also that of hundreds of thousands of others within a region encompassing hundreds of millions of light years. The cumulative effect of all the mass, visible and dark, on these galaxies' motions reveals the deep gravitational architecture beneath the sprawling cosmic landscape. Looking deeper into the heart of the Great Attractor region, the dynamics of galaxy clusters there offer clues about the processes that gravitationally bind such large structures. Over billions of years, smaller groupings of galaxies merge under mutual attraction, building up massive clusters that become luminous in X-rays due to the hot gas trapped within. This gas, heated to millions of degrees from the energy released during mergers and from the gravitational potential, creates the bright X-ray signals that observatories detect. The interplay between gravity pulling galaxies and gas together, and mechanisms that can strip gas away during collisions, plays a crucial role in galaxy evolution within these clusters. Gas is a vital ingredient for star formation, so when it's removed or heated, star formation can be suppressed, altering the development of galaxies over time. Studying this balance provides insights into how the dense environment near the Great Attractor shapes the galaxies caught within it. Despite the progress, many questions remain about the full extent and detailed structure of mass concentrations like the Great Attractor. Observations continue to improve with new technology, gradually revealing a more nuanced picture. For instance, the exact contribution of dark matter clumps versus visible matter in the gravitational pull remains a complex puzzle. Each layer of understanding sheds light on how the universe organizes itself. On the cosmic horizon, efforts to survey fainter and more distant galaxies promise to place the Great Attractor within an even broader context. As our maps extend further, we begin to see how these clusters form just one tier within a hierarchy of cosmic structures stretching across billions of light years, shaped over the lifetime of the universe. Reflecting on the journey so far, the Great Attractor stands as a remarkable example of how scientific inquiry can reveal hidden giants in the cosmos. What began as an anomaly in galaxy motion gradually unfolded into an elaborate structure that has reshaped our understanding of the local universe. It combines the influence of dark matter, galaxy clusters, intracluster gas, and the larger cosmic web in a gravitational symphony guiding the movement of many galaxies, including our own. Each new discovery about this region not only advances our knowledge of local cosmic dynamics, but also contributes to the broader quest to understand the universe's composition, history, and ultimate fate. Through the lens of the Great Attractor, astronomy demonstrates how even seemingly abstract motions of distant galaxies offer clues to the fascinating and interconnected nature of the cosmos. The story of the Great Attractor also draws attention to one of the most puzzling components of the universe: dark matter. Although invisible and undetectable through traditional means like telescopes that rely on light, dark matter exerts a gravitational pull that shapes the structure of the cosmos at every scale. Within the region of the Great Attractor, the influence of dark matter is especially significant. The enormous gravitational well pulling our galaxy and many others can't be explained solely by the visible stars, gas, and galaxies we observe. A large fraction of the mass responsible lies in the dark matter holding these structures together. Dark matter acts like an invisible scaffold, creating the gravitational backbone around which galaxies and clusters form and evolve. It neither emits nor absorbs light, so scientists infer its presence by observing how visible matter moves. For example, galaxies near the Great Attractor move faster than would be possible if only their visible mass were exerting gravitational force. This discrepancy points to a substantial amount of unseen mass, dark matter, within the region. Further evidence for dark matter around the Great Attractor comes from studies of galaxy clusters' hot gas. When astronomers analyze the X-ray emissions from this gas, they discover that the hot plasma is bound within the gravitational field of a much larger mass than what's visible. Calculations show that dark matter must be present to account for both the temperature of this gas and the overall stability of clusters. Understanding the role of dark matter here also helps us refine cosmological models. Simulations of the universe's structure formation repeatedly show that areas like the Great Attractor, where mass accumulates rapidly, correspond to dense concentrations of dark matter. These simulations start with the early universe's nearly uniform distribution of matter, and, over billions of years, evolve into the complex cosmic web marked by filaments, voids, and clusters. The Great Attractor is one of these dense nodes where mass has gathered through billions of years of gravitational collapse. Another key player in these regions is dark energy, an even more mysterious force causing the universe's expansion to accelerate. While the Great Attractor is a gravitational well drawing galaxies inward, dark energy is pushing the universe outward on larger scales. This dynamic tension between gravity's inward pull and dark energy's outward push shapes the ways galaxies move relative to one another. Interestingly, because the Great Attractor's gravitational influence extends over hundreds of millions of light years, scientists must consider both local and large-scale effects. The universe on these scales behaves like a complex fluid of matter and energy, with clusters and superclusters establishing gravitational flow patterns. However, dark energy steadily expands space itself, slowly pulling galaxies away from each other on the grandest scales. The balance between these forces adds a layer of complexity to predicting the future paths of galaxies involved in the Great Attractor's sphere of influence. In addition to dark matter and dark energy, the Great Attractor region also contains numerous galaxy clusters and superclusters, behaving like cities within an interconnected metropolis. The most prominent structure in this area is the Norma cluster, a massive and richly populated cluster of galaxies that sits near the heart of the Great Attractor. It is one of the densest galaxy concentrations known and has been a prime focus for astronomers attempting to identify the specific sources of the enormous gravitational pull. The Norma cluster's gravitational field helps explain much of the observed flow of galaxies in our cosmic neighborhood. Over millions of years, clusters like Norma attract smaller groups and individual galaxies into their gravitational embrace. The gradual process of clusters merging is fundamental to how the large-scale structure of the universe evolves. When two galaxy clusters collide and combine, the event releases tremendous amounts of energy, reshaping the galaxies and the hot gas trapped between them. Studying clusters such as Norma provides a window into several physical processes, including the stripping of gas from galaxies during close encounters, the effects of high-speed collisions, and the complex interactions in the dense, hot gas filling the space between galaxies, known as the intracluster medium. These phenomena influence the growth, star formation, and eventual fate of the galaxies caught in clusters' gravitational grip. Beyond the Norma cluster, the Great Attractor region also connects to larger-scale cosmic structures. It lies within a supercluster complex that includes the Hydra and Centaurus clusters, which collectively contribute to the gravitational landscape. The combined gravitational effects of these massive clusters help to generate the coherent motion pattern observed in galaxies over this region of space. Mapping these flows is similar to charting ocean currents on Earth, but on incomprehensibly larger scales. Imagine measuring how millions of galaxies flow, some drawn inward toward gravitational sinkholes like the Great Attractor, others moving away from vast, empty cosmic voids that stretch for hundreds of millions of light years. These maps not only reveal the locations of enormous mass concentrations, but also expose the large-scale architecture of the universe. One enduring challenge in understanding the Great Attractor involves regions obscured from clear observation. Part of the mass lies hidden behind the plane of our own Milky Way, where dust clouds and stars block our view in visible light, a zone astronomers call the zone of avoidance. To overcome this, researchers turn to other wavelengths like infrared and X-rays, which penetrate dust more effectively. Using such observations has revealed more about the hidden structures contributing to the gravitational pull. These advances have helped clarify the Great Attractor's composition, but even larger and more massive structures beyond it have since been discovered. For example, the Shapley supercluster, farther away than the Great Attractor, is a still more massive concentration influencing local galaxy flows to some extent. Understanding how these multiple attractors interact and the scale of their combined influence remains a subject of ongoing research. As we refine our picture of the Great Attractor and its surrounding structures, we gain a better grasp of our place in the cosmic web. Our galaxy, the Milky Way, is not stationary. It participates in a complex set of motions caused by the gravitational tug from this vast region of space. In total, the Milky Way is moving at roughly 600 kilometers per second, about 1.3 million miles per hour, relative to the cosmic microwave background, the leftover radiation from the Big Bang. This motion is influenced heavily by the mass concentrations within and beyond the Great Attractor region. Furthermore, this motion affects how astronomers interpret observations of the universe. Our velocity relative to the cosmic background creates a dipole anisotropy, a slight change in temperature in the cosmic microwave background radiation when viewed in different directions. This subtle effect, measured with great precision by missions like the Cosmic Background Explorer, COBE, and the Planck satellite, provides independent confirmation of the Milky Way's movement and helps calibrate cosmic distances and velocities. One might wonder what the long-term future holds for galaxies caught in the Great Attractor's gravitational web. Ultimately, gravity will continue to draw galaxies together, merging smaller groups into larger structures. Over immense timescales, clusters like those in the Great Attractor region may coalesce into massive superclusters or gravitationally bound groups, sometimes dubbed megaclusters. However, the accelerating expansion of the universe, driven by dark energy, means that, on the largest scales, these massive structures will become increasingly isolated. While gravity on small scales dominates and binds groups and clusters, the space between these large lumps will stretch, causing many galaxies to move beyond the reach of each other's gravitational pull. This interplay of attraction and expansion shapes the future cosmic landscape. It suggests a destiny where local clusters remain bound together, but distant ones accelerate away, becoming unreachable as the universe ages. For now, though, the Great Attractor remains a gravitational focal point, shaping the motions of galaxies, including our own, and serving as a crucial feature in the ongoing quest to map and understand the universe. As new telescopes and instruments come online, capable of detecting subtle signals and mapping the cosmos more deeply, we will continue to unravel the mysteries around the Great Attractor. Each discovery not only illuminates the nature of this massive structure, but also adds to a broader narrative, the story of how matter clumps and flows across billions of years to form the network of cosmic islands that populate space. In piecing together this story, astronomers gain insights into fundamental questions about the universe's composition, its past, and its future, with the Great Attractor serving as a key chapter along the way. While the Great Attractor is indeed a powerful gravitational anomaly drawing galaxies toward it, the story doesn't end there. Understanding its nature necessarily leads us to consider the very composition of the matter it's pulling together. When we speak about mass in the universe, we often think first of the stars we observe in galaxies. However, the visible matter, stars, gas, dust, that we detect with regular telescopes accounts for only a small fraction of the total matter in the cosmos. This brings us to one of the biggest puzzles in modern astrophysics: dark matter. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, rendering it invisible to the instruments we commonly use. Despite this invisibility, dark matter exerts gravitational forces, and we infer its presence from these effects. In the case of the Great Attractor, a significant portion of the mass responsible for pulling on our galaxy and neighboring ones is believed to be dark matter. The unseen scaffolding of dark matter helps to bind together the clusters and filaments we detect through visible light and other wavelengths. Scientists observe the influence of dark matter on galaxy clusters and the cosmic web via gravitational lensing, where the gravity from a massive object bends the path of light from more distant sources, and through the peculiar velocities of galaxies moving within clusters. These velocity patterns don't add up if we consider visible matter alone. The influence of dark matter must be factored in. Without it, the clusters wouldn't have sufficient mass to hold themselves together against internal motions. In the context of the Great Attractor, combining the mass of visible galaxies, hot gas detected in X-rays, and dark matter yields a comprehensive picture of the enormous gravitational weight this region has in the large-scale structure of the universe. It also explains why local motions aren't random, but instead display a consistent flow toward this concentration of mass. But dark matter is not the only piece adding complexity to the Great Attractor puzzle. There is also the role of dark energy, a mysterious form of energy permeating all of space and driving the accelerating expansion of the universe. While gravity pulls galaxies inward, Dark energy pushes on the larger cosmic scales in the opposite direction, causing distant galaxies and clusters to accelerate away from one another. This dual influence shapes the universe's large-scale structure, determining which clusters merge and which become isolated as accelerated expansion outpaces the gravitational pull. Looking beyond the Great Attractor, astronomers have identified even larger structures influencing galactic motions and the universe's architecture. One such structure is the Laniakea supercluster, a gargantuan collection of galaxies that includes the Milky Way and extends across over 500 million light-years. The Great Attractor sits roughly near the heart of Laniakea's gravitational basin, playing a critical role in the flows of galaxies within this supercluster. This redefined understanding was an important breakthrough in cosmic cartography, showing that our Milky Way is part of a far larger, interconnected cosmic system shaped by gravity on immense scales. Interestingly, the Great Attractor itself appears to be just one part of an even more complex network of mass concentrations and voids. Voids, vast, low-density regions, exert their influence by effectively pushing galaxies away, while clusters and superclusters like the Great Attractor pull galaxies inward. This push and pull across different regions collectively shape the cosmos's intricate web-like structure. The challenge of mapping and understanding these enormous structures lies in the limitations of our observations. Much of the Great Attractor region remains difficult to study because it is obscured by the dense disk of our Milky Way. However, advancements in multi-wavelength astronomy continue to reveal the hidden mass within and beyond this zone. For example, the use of radio astronomy to study the hydrogen emission line at 21 centimeters permits detection of galaxies even through thick dust and gas lanes, providing critical data points in this otherwise hidden galactic landscape. Another avenue where new insights may emerge is the study of gravitational waves and neutrinos. While these phenomena are still in their infancy with respect to mapping large-scale universe structures, the sensitive detectors currently operational and being developed hold the promise of probing cosmic events taking place in distant clusters. Understanding the mergers of massive black holes or galaxy clusters through gravitational waves could offer indirect information on the mass distribution and dynamics in areas associated with the Great Attractor. Moreover, computer simulations and cosmological models have become a key tool for piecing together the nature of the Great Attractor and its surroundings. By starting with initial conditions consistent with observations of the early universe, such as the cosmic microwave background radiation, and letting gravity and expansion evolve structures over billions of years, these simulations can recreate distributions of galaxies and clusters resembling those we see today. This approach allows researchers to test hypotheses about how and why such enormous structures like the Great Attractor formed, and how they influence the motion of galaxies. As models become ever more sophisticated, they help answer deeper questions about the role of dark matter and dark energy in sculpting cosmic structure. They also provide insights into the timescales over which superclusters evolve, merge, or break apart. Such knowledge is vital for understanding the future trajectory of our galaxy and its neighbors, whether they will remain gravitationally bound or be gradually carried away by cosmic expansion. In addition to the large-scale cosmological context, the Great Attractor also raises intriguing points about what it means to pinpoint our galactic coordinates and motion in the universe. Locally, the Milky Way is part of the local group of galaxies, including Andromeda and smaller neighbors. This group orbits around the Virgo cluster, itself a massive collection of galaxies forming the central part of the Virgo supercluster. Beyond that lies the region dominated by the Great Attractor. By tracing our galaxy's motion relative to these reference points, astronomers refine their understanding of the Milky Way's past journey and future path. The velocity of roughly 600 kilometers per second relative to the cosmic microwave background is an aggregate result of multiple gravitational influences, with the Great Attractor playing a dominant role alongside other mass concentrations like the Shapley supercluster. This complex dance of cosmic gravity and expansion is an ongoing area of investigation, revealing new surprises as data accumulate. With missions such as the European Space Agency's Euclid telescope set to launch in coming years, aimed at mapping the distribution of dark matter and dark energy in unprecedented detail, the Great Attractor and its cosmic environment will be studied with sharp new eyes. This refined understanding echoes a central theme in astronomy: that no object exists in isolation. Just as planets orbit stars and stars orbit galactic centers, galaxies themselves are bound within larger gravitational tapestries. The Great Attractor is one of the dominant nodes within this web, a beacon illustrating how gravity shapes the universe over immense scales of space and time. The journey to fully grasp the Great Attractor continues, with each discovery providing crucial data about how matter congregates in the universe, how galaxies move, and how forces like dark matter and dark energy sculpt the cosmos. It stands as a remarkable example of how modern science pushes beyond visible horizons, using a combination of observational ingenuity and theoretical modeling to uncover the hidden forces shaping our galactic neighborhood and beyond. As our understanding of the Great Attractor deepens, one of the most intriguing questions remains: what exactly lies beyond it? Is there a greater cosmic structure influencing the motion of entire superclusters and defining the large-scale flow of galaxies over hundreds of millions of light-years? Astronomers have long suspected that the Great Attractor itself is part of an even larger gravitational anomaly. Subsequent research pointed to the existence of what is now known as the Laniakea supercluster, a titanic cosmic structure comprising the Milky Way and tens of thousands of other galaxies, all moving within a shared gravitational domain. Discovered and named in 2014, Laniakea, which means immense heaven in Hawaiian, redefined what we considered the boundaries of our cosmic neighborhood. Prior to this, the Virgo supercluster was regarded as the local supercluster encompassing our galaxy. But by carefully mapping the motion of galaxies and their velocity flows through redshift surveys, astronomers delineated a vaster region governed by gravitation centered roughly on the Great Attractor. This new perspective illustrates that the Great Attractor is not an isolated mass concentration, but rather the focal point of a sprawling network of clusters and filaments threading through the cosmic web. The cosmic web itself is a large-scale structure that stretches across the universe, composed of vast voids surrounded by filaments of galaxies and clusters, shaped by the interplay of gravity and the expansion of space. These filaments act like the scaffolding upon which galaxy clusters form. The Great Attractor represents a major node where several such filaments intersect, gathering enormous amounts of mass. Its gravitational pull causes galaxies within Laniakea, including the Milky Way, to flow inward, akin to water funneling toward a drain, but on scales that boggle the imagination. Mapping these flows involves piecing together the velocities of galaxies relative to the cosmic microwave background, and then tracing the direction and magnitude of their peculiar velocities, movements deviating from the general expansion of the universe. When these data are plotted carefully, they reveal coherent bulk flows converging toward the Great Attractor region, offering a three-dimensional map of the gravitational landscape. However, even Laniakea's extension may not be the full story. Beyond lies an even more massive concentration linked to the Shapley supercluster, located approximately 650 million light-years away. The Shapley region is one of the most massive structures in the nearby universe and appears to exert additional gravitational influence, affecting the motion not only of galaxies, but entire clusters across an immense volume. This subtle tug from Shapley causes deviations in the inflow toward the Great Attractor, suggesting a complex interplay of massive structures pulling on galaxy flows. Observations at multiple wavelengths, extending far into the infrared and X-rays, continue to peel back the layers of obscuration in this region. X-ray telescopes like NASA's Chandra and ESA's XMM Newton have revealed hot gas permeating massive galaxy clusters near the Great Attractor, providing clues about their mass content and dynamical state. Since clusters contain a significant fraction of the universe's mass in the form of dark matter, mapping their distribution is key to understanding the underlying gravitational omnipresence shaping the motions we observe. The role of dark matter is absolutely fundamental when considering structures like the Great Attractor. While ordinary, baryonic matter, stars, gas, and dust, is responsible for the visible light we see, it comprises only a small fraction of the total mass in large-scale structures. Dark matter, which neither emits nor absorbs light, is detected only through its gravitational effects. It forms an invisible halo that dominates the mass budget of galaxies and clusters, influencing how matter clumps together over cosmic time. This insight emerged from decades of studying galaxy rotation curves, gravitational lensing, and the cosmic microwave background, all pointing to a universe permeated by unseen matter. The Great Attractor region, likely containing vast quantities of dark matter, serves as the gravitational engine behind the observed galaxy motions. Without the added mass dark matter provides, the accelerations and velocities of galaxies toward the Great Attractor would be difficult to explain. Simultaneously, dark energy, the mysterious force causing the accelerated expansion of the universe, plays a contrasting yet interconnected role in this cosmic dance. While gravity pulls matter together, dark energy drives regions to move apart on the largest scales. Intriguingly, the Great Attractor and its surrounding superclusters lie near the boundary where gravitational attraction of dense matter concentrations begins to overcome the repulsive effect of dark energy. This interaction defines the future fate of these structures. Will they remain gravitationally bound, slowly merging into grander clusters, or will cosmic expansion eventually dilute their gravitational grip? Current models suggest that on galaxy cluster scales, and even somewhat beyond, gravity reigns supreme, allowing superclusters like Laniakea to persist as coherent structures for billions of years. However, beyond these domains, dark energy's influence dominates, accelerating the universe's expansion and pushing galaxies farther apart, fragmenting the larger cosmic web over time. Our own Milky Way, part of this gravitationally bound supercluster system, is slowly heading toward a spectacular collision with the nearby Andromeda galaxy, expected to occur in about 4 billion years. Both galaxies are participants in the broader flow toward the Great Attractor. Yet their mutual orbit and eventual merger occur on local scales, vastly overshadowed by the immense motions influenced by large-scale structures. This hierarchy of gravitational effects, from galaxy pairs to clusters to superclusters and beyond, underscores the layered complexity of the universe's architecture. Looking ahead, ambitious survey projects and observatories continue to sharpen our view of the Great Attractor and its cosmic context. For example, the Dark Energy Spectroscopic Instrument, DESI, is mapping millions of galaxy redshifts over a huge volume of space, aiming to refine our understanding of galaxy clustering and dark energy's role. Additionally, next-generation X-ray observatories like Athena, planned for the 2030s, promise unprecedented sensitivity in detecting the hot gas in galaxy clusters and filaments, further clarifying the structure and mass of the Great Attractor region. Meanwhile, gravitational wave astronomy, still in its infancy, offers a complementary avenue to probe the dense environments of massive black holes in cluster cores, mergers detected by LIGO and Virgo on Earth, and in the future by space-based detectors like LISA, could yield indirect insights into the growth and dynamics of massive structures linked to the Great Attractor. This convergence of data streams and technologies is transforming the Great Attractor from a mysterious gravitational anomaly into a well-characterized node within the cosmic web. It exemplifies the power of multi-messenger astronomy, combining electromagnetic observations, gravitational waves, and particle detections to unravel the physics of the universe on both local and grandest scales. At its core, the study of the Great Attractor touches on profound themes about our place in the cosmos. By retracing the paths galaxies take, we learn about the invisible forces sculpting the universe and glimpse the long history of cosmic evolution shaped by gravity, dark matter, and dark energy. Our journey through space is not random, but rather guided by the inexorable pull of massive structures like the Great Attractor. In this sense, the Great Attractor is more than a gravitational sticker exerting force on our galaxy. It is a testament to the interconnectedness of all matter on the cosmic stage, revealing how even the immense Milky Way is caught in the flows of a dynamic, evolving universe. The more we study it, the more we appreciate how much remains to be understood, urging a continued quest to illuminate the dark corners of our universe and understand the fundamental forces governing its grand architecture.